嗯 test test，我先介绍一下，然后把这个给你，点一下这个，在这个屏幕上，你把对对对，OK，嘿啊，Hey, sorry for the delay. Welcome to this talk. It's my pleasure to introduce our speaker, Matthew Hong. Matthew is a final year PhD student at MIT, advised by Bonnie Berger and Kalai. He is interested in applied and theoretical cryptography. His research on privacy-preserving generic nearest neighbor search received the Best Student Paper Award at RECOM 2024. Matthew received his Bachelor of Engineering from the Institute for Interdisciplinary Information Science at Tsinghua University. Okay, without further ado, the stage is yours. Yeah. 你看 Yeah, that's our.
Uh, Good afternoon. Thanks for the invitation. Today I want to share a recent preprint. It's about the title is toward a doubly efficient IP equals PSPACE, and it's joint work with my amazing co-authors Lian Chen, Yael Kalman Kalai, and Zoe C. They are all at MIT. And so let me first define what's going to appear in the talk. If anything is unclear, feel free to interrupt me. Um, so as you may have heard, interactive proofs, also known as IP, is introduced a long time ago, and it's very useful, very influential notion in complexity theory and cryptography. In our work, we focus on the setting of public coin interactive proofs, where we have two parties. One of them is called Merlin. He's also the prover, and usually it's depicted as being all-powerful but untrusted. And the second party is Arthur. As you can see, he's a weak polynomial time machine, depicted by this angel on the right. And in theoretical computer science, we usually have some input x, and we denote its length as n. And their goal is to jointly verify that some x, the input belongs to some language L. Um, and concretely, you can think of L as like some NP hard language, like three coloring, and X would be a graph. And this like checking whether X belongs to the three colorable graphs would basically be an NP hard problem, which is very difficult. But it turns out with interaction and with this all-powerful entity, you can still verify it with an efficient polynomial verifier. And usually, in our in our model, let us assume the protocol goes in rounds, where the author sends some public coin that are sampled one at a time in each round. Sorry, I shouldn't. Um, sorry, 1 second. Let me make sure it won't appear again. Hmm, I can't find my mouse. Okay. Okay. Yes, so let me repeat what I said. Arthur will sample some random coin Q in every round, and he will send the random coin to Merlin, and Merlin will respond by some answers. The answer would not be a random coin; it will be something computed by Merlin, and it will go on for L rounds. In the end, Arthur will apply some polynomial time algorithm V on the input X, as well as the entire transcript that consists of all the queries and all the answers. And using this polynomial time check, Arthur will decide whether to accept or to reject the statement. Basically, it means whether Arthur believes that X is decouplable or not. And we require two properties of interactive proofs to be non-trivial. The first property is called completeness. It says if belongs to the language L, then there should exist some honest prover P or Merlin such that after the interaction, the probability that Arthur accepts the statement is 1. And for soundness, we require that if the statement is actually false, for example, the graph is not really three-colorable, then no matter what the cheating strategy of the prover is, like even if it's unbounded or powerful, running in infinite time, it will still be unable to convince Arthur to accept the statement. And formally, we require the probability that Arthur accepts to be bounded about by a half. And the probability is over the randomness of the public coin. Okay. And this famous result that if you take complexity in undergrad, you must have learned it. It's called IP equals PSPACE. It's a very famous result by Shamir. It says any language that is decidable in polynomial space actually emits a protocol where the verifier runs in polynomial time. So even though the language itself might require exponential time to compute, you don't need to rerun the computation if your goal is to just verify the output is correct. Like you don't have to really do the computation again.
Why are also citing LFK?
Oh, I think it's because they introduced this very powerful tool called SumCheck, and it's heavily used in Shamir's protocol. Yeah, but I guess there are a lot of citations that I missed too. So these are the two that are most relevant. Any other questions? Okay. If not, I'll introduce our main goal in this work. It's called doubly efficient interactive proofs. Basically, our goal is to verify a Turing machine computation is correct. Maybe the input is x of length n, and the Turing machine time is t of n, is a function in n, and s is the Turing machine space. And our target is to verify such computations with an efficient verifier. So it's very similar to what I just described. But we really care about the actual efficiency of the verifier and the prover. And in particular, our target would be to have a prover whose running time is almost the same as the computation itself. There's almost no overhead on top of the computation itself. So it's called proving as fast as computing. And verifier time would be roughly reading the statement itself, and it's like proportional to the space of the Turing machine. And I coined this term with the help of GPT. It's called Provolone. It's a dreamland where such things are possible, but still, we haven't reached it yet. That's why we called our paper towards a doubly efficient IP equals PSPACE because we are making like one step towards the goal. And you may wonder why the result that I mentioned by Shamir, IP equals PSPACE, why wasn't that already a solution to this problem? It's because Shamir's protocol, even though it can handle such computation, um, it allows the verifier to run super efficiently in time that's Sn, that's roughly Sn, but the prover time is not T of n, it's actually T 2 to the Sn or even larger. So if n is linear, this is already exponential, but we really want something that's like closer to the actual computation time t and not 2 to the n. And there's also this second related line of works. It's called computationally sound proofs or arguments. There we relax the soundness guarantee to hold only against computationally bounded provers. And we also require some cryptographic assumptions. If you allow that setting, then this problem is also solved. But we really want to challenge ourselves and study complexity limits of our human knowledge. So our focus would be to have protocols that are secure against even computationally unbounded provers. So they are usually called proofs as opposed to arguments.
So if you're talking about arguments, I guess it doesn't make sense to say IP, right? As long as you can do that for NP, that's good enough already. For arguments.
Uh, Depends on who you ask, I guess. So I guess you can also study can we get a argument systems for exponential time or something that might be larger than NP.
Your malicious prover will only be polynomial.
Oh, yeah, that's a very good point. Yeah, I guess okay.
But anyway,
Yeah.
if we don't know if NP equals IP or not. This is an open question. So assume it's not. I'm just saying that the thing in the middle actually cryptographers don't care. The thing in the middle.
Yeah, I think that's true. Yeah. But here we require the prover to be efficient, but the malicious prover to be unbounded. So it's kind of the other direction. And I think this is interesting because cryptographers seldom sleep well at night. And with this, we can sleep well at night. We don't require assumptions. Okay, any other questions about the general setting? Okay, if not, I'll dive directly into some technical stuff. Don't worry if you don't follow everything. This is just to give you a taste of how such protocols are constructed. And this is I think the first general model for such doubly efficient interactive proof settings. And it's called a GKR protocol. And the computation model, as opposed to Turing machine, is circuit. And the top layer would be the output node, and the input layer would be in the bottom. And you write the input bit by bit, x1, x2, up to xn. And then the goal is to verify that the circuit outputs 1 if you feed in some particular input. So trivially, the verifier could have just evaluated the circuit on its own. That would require time proportional to the size of the circuit. But you can imagine such a protocol where instead of evaluating the entire circuit, verifier now has access to some short description of the circuit. Maybe it's very structured. So the verifier can query whether some local gate is an AND gate or an OR gate and something like that. So it doesn't take time to index into a circuit. So the verifier now wants to verify the output is 1. If it's an AND gate, then it's true only if and only if both of its predecessors, the input bit to that gate, are both 1. And but now the verifier, instead of verifying both of the input bit, it randomly chooses one of the two branches and then verify only that branch. So this is going to create some issue, as you might have realized. But let us move on with this idea. We just randomly pick one branch every time. And for the next layer, we do the same. And in the end, we end up with some local constraint about one input bit. And maybe it says x3 should equal to 1. And the verifier only check these properties. And as you can see, this is going to be very problematic because the prover might be cheating on exactly one of the branch, and almost everywhere else it's going to be locally consistent. Yeah, I think is everything clear now? So basically, the verifier wants to verify the output is 1. It would ask the prover to review the values of the circuit one by one. Instead of checking all the intermediate values, it's going to verify only one of the branch. but the issue is prover might only lie on one branch, and you have like exponentially small probability of choosing that particular branch, and everywhere else it might be correct. In that case, you only have like almost zero probability of catching a cheating prover.
I think I assume this is the exponential size. Okay.
Let us assume everything is polynomial. The goal here is to get something that's smaller than the size of the circuit.
Ah,
Yes. But later on we'll relax this and everything will be a general functions of n. So here maybe think of the circuit as being very, very wide and the depth is very small.
it's just that in this model, I think your verifier needs to know the description circuit.
Yes,
If it's polynomial size, then there's no problem. But I guess later you need extra techniques to make it.
indeed. So for example, it, this is actually going to be a component of our protocol. We are going to use it as a black box, so you don't have to understand how it works. But because we are working with Turing machine, there's this Cook-Levin reduction that transforms the consistency check of Turing machine into consistency check of a corresponding circuit. Um, so you can think of the circuit as like being really exponential size if the Turing machine runs in exponential time. But you actually have a very short description of the circuit. It's the description of the Turing machine itself. Yes. So in that case, you can apply this protocol. Okay.
That means you have to choose Turing machine as your model. It doesn't work if you use circuit in your results.
I think we are, sorry, can you be more, what do you mean by
If
it
you
doesn't work?
this technique, the circuit only has a succinct representation.
Yes.
The Turing machine model. I'm asking, can you
Can
if
approve
I'm
a,
thinking about okay, can you give me a doubly efficient IP equals PSPACE, but using circuit as conventional model? Then your result doesn't imply that.
so
Because
you,
in that regime, you won't have a succinct description of the circuit if the circuit itself is a exponential sign.
yeah, but in that case, I think it's a bit ill-defined because the verifier doesn't even know the circuit. Yeah. Yeah, but I can imagine in blockchain applications, people think of this as maybe the blockchain, and then you have this like current hash of blockchain status. And
I think you can always hash everything.
yeah, yeah, yeah,
Yeah,
yeah.
yeah. I don't think that's an issue.
Yes.
But I see your point there. I shouldn't ask this question for circuit model because the circuit itself is already exponential size.
Mm. Yeah, I think, but indeed, yeah, I'm not very sure about whether there could be broader classes of circuit that we can support. Currently, we know how to support circuits for log space uniform descriptions. So this is exactly what GKR does. Yes, but I guess the baseline protocol that I described it's clearly not sound and insecure in the sense that we only have almost zero chance of catching a cheating prover. And in the actual construction, they use error correction, which some good codes that spreads local inconsistency into many inconsistencies. So you can expect maybe there's one half of the of the messages in each layer is going to be incorrect. So in some sense, you're always going to catch a cheating prover. Yeah, so they are encoding all the values of every layer using some error correcting code. And instead of asking the prover to send the actual values of the wires, it's going to ask it to send some code word values of that layer. And then they also have this reduction protocol, which relies on some check. So it basically relates the consistency of two layers by having some interaction. And they write the consistency relation as some polynomial relations, and some check allows you to verify such relations. And then you run this reduction for L steps, for D steps. In the end, the verifier only had to verify one point of the input encoding. And then this is the entire protocol if you think of everything as a black box. And you may object that the verifier doesn't have access to the input encoding, but you can think of it as as our model assumption. The verifier has some access that's trusted for the input layer. Okay, so to be more formal about what this protocol does, the statement goes as follows. It says for every log space uniform circuit C of depth D and the size is G, there exists some special kind of interactive proof. It's called low depth predicate interactive proof. It proves that the circuit output some value Y. And in this protocol, the approval running time is proportional to the size of the circuit. Maybe there's some polynomial dependency. The verified running time is roughly the depth of the circuit and multiply with some polylog factors of the size. So it's going to be super efficient if the depth is small relative to the size. And it's very important. If you look at the actual protocol GKR, the verifier doesn't ever access the input X until the very end. And in the end, it only makes its decision on whether to accept or to reject based on some low depth circuit psi. And this circuit is of polylog depth. We are being very sloppy polylog in G and N and everything else. But yeah, that's probably the idea. And it's only this circuit that's going to access the input encoding. Everything else done by the verifier in the protocol is not going to touch the input X. So this is the result by GKL phrased in our current setting. Okay. And we are going to use this special kind of protocol as a black box. It's going to be our building block, and we can build our Turing machine verifier using this protocol. Okay. Any questions so far?
So I'm not very familiar with this, but I want to ask. So according to your description of the previous slide, the algorithm you build sounds like an almost correct, like correct most of the time. So is it like always correct or like almost?
By correct, you mean catching the prover. It's going to be bounded. So a cheating prover would have a chance of succeeding bounded about by a half. Yeah, but you can make it almost zero by repeating. Yeah.
Can one view like where do they actually do the conditions log space uniform? Click. Is this has anything to do with what we just discussed? Like you need a succinct description, right?
Yes, yes. So it's something like it's this reduction protocol. You want to, if it's an AND gate, you would without all the encoding thing, you want to verify the input are both one, right?
Yeah.
Like if it's one, you want to verify both are one. And but with the encoding, it actually looks like some polynomial relation. So two polynomial agrees on some points, maybe that's the statement. And the coefficient of a polynomial, you need to somehow generate it efficiently. And if you have a short description of the circuit, then you can generate those coefficients. I think that's roughly it. Does that answer your question?
Yeah, then when you say log uniform, actually as long as it's when we say log uniform, we mean for any log space Turing machine. But actually that log can be just a log on circuit side. That means if I have a circuit of like n, as long as I have like space log and Turing machine to generate circuit, then the theorem always apply.
Yes, I think so. But it's just the way it's written, it's currently very sloppy. Maybe there are some additional terms depending on this circuit that generates the description the description.
This setting, you see the verifier's time is smaller than the size of G.
Yes.
That means the verifier doesn't really read the circuit.
No, because it's very similar to this one branch checking. It's just going to generate the coefficient that it needs when it compute this reduction. So
But my point is, they at least they need to agree on what they are proving, right?
yes,
That translates to encoding of the circuit. I think it's just like multi-linear extension of the circuit, right?
yeah.
So if you want to still do this, you need to assume that the verifier holds the MLE of the circuit. It's not only the MLE of a certain gates, right? It has to hold for the whole circuit.
You mean the description, or
Yeah.
I'm not sure if that's necessary. Mm, why do we why does the verifier need the MLE of the circuit?
For example, if this circuit is special such that as long as I flip one gate, for example, if I replace one AND gate by a multiplicator gate, then I can flip the output. In that sense, the prover, like if the verifier doesn't hold the whole description of the circuit, they won't be able to distinguish between these two cases. When he's talking to a prover, yes, they are starting to do things about the MLE of something. But how do the verifier know that you are giving me the MLE of the correct circuit, not the at all?
So maybe the difference is the prover is sending not just the wire values, it's sending also potentially something outside the wire values. So when you encode the layers, you're encoding it over some larger field. So what the prover sends actually contains information about every value on that wire, on that layer.
Yeah, but if you go to next page, this theorem, information theoretically, I feel you need to add some G on the very first runtime. Unless when you are counting the very first runtime, you don't count the time it used to read the X. Oh, sorry, to read the circuit.
So yes, actually there's some term that I'm missing. For example, you need to add the description size of the circuit.
Yeah.
Yes. Yeah, I see. So it's actually there. I just don't want to complicate the statement. Yeah. Yeah, and if you look at the paper, it's very messy. So this is very annoying too.
Basically, I would naturally I would expect it to be like something like a log time uniform. Then you are saying anyway they use space as a measure. This is a condition. If it's log space uniform, then you can do MLE efficiently. Otherwise, you can't. Not true.
MLE. Yes, so I think the actual, I'm not 100% sure, but I think the original GCal has something slightly more general than log space uniform. But then it turns out
the log space is too relaxed because log space is like exponential time. But no, it's linear time. Your log space is already linear time. Linear time sounds bad because you want to avoid linear time for the verifier.
Let me think.
I guess something hidden in this one. When I'm saying that this predicate computes over ECC of X, I mean ECC of X need to be well defined so that a well defined ECC on X, the verifier at least needs to know the full X.
Yes. So you also have to add the length of the verifier.
Input.
Yeah.
Okay, sure.
Yeah, but here I just count the verify runtime before this check. So there's a plus n, but this plus n doesn't appear in this expression. Yeah, it's because I postpone my decision to the circuit. So this is actually a very important distinction. the verifier doesn't access X until the very end where it gives you a predicate. Yeah. Okay. But yeah, to your point, I think the log space uniform thing, I'm not entirely sure it's very super studied deeply. It's just something that we know works, and it's also nice if you assume it. It doesn't complicate things too much. Yeah. But I think there's no reason to assume that's the best circuit class that we can support. Okay.
I mean, this is the information theoretical lemma. That means if your G is double exponential size, it's still true, right? So that
I think so, yeah.
yeah, then I'm not sure if the log space. I mean, when I adjust the size of G, should I also adjust the log space part?
Yes, I think that's the messy part. Yeah, when we write our paper, we also have to handle such things, and we try to keep it readable. It's very like the log space. Usually we think of it as the log of the circuit size, but here we have an additional input, and if you allow the things to have too many degree of freedom, I think you have to really maybe recompute all the terms from the paper. Yeah.
There's no like short closed form expression. For example,
Mm.
I cannot say no matter how large G is, you can always use the log G space uniform. That's not true. I need to do a more careful calculation.
At least I'm not convinced that you can just say that it's true. But like for example, GKL phrase G as a polynomial in N, then in that case they are the same. Yeah. Okay. Okay. Assuming that we roughly understand our model, we can dive into a very high level idea how our construction works. It's going to be based on recursion. And in the previous work, we have some very complicated double recursion. Here we simplify it slightly, but it's going to have a very similar idea. Our goal, we are working with Turing machine now, so our goal is to verify some input tape, sigma 0. It's X followed by some number of 0. If you run the Turing machine on this tape, you're going to get the accepting tape, which is 1 followed by another string of 0. And you're running it for exactly t steps. So this is just rewriting what we mean by Turing machine verification. And usually, so in our setting, it would be very helpful if we think of the hidden transition, which is depicted by the arrow here, and that it's the tableau of a P times S size. It's a hidden matrix as the witness of this particular statement. So there's no reason why it has to be a witness. The original thing is not an NP statement, but it's just the terminology that we'll use. But you can see why we use the term witness later. And the idea from a paper from 10 years ago, Rothblum, Ringo, they break this transitions problem into K parts. Instead of verifying the claim in one shot, you're going to verify K claims separately. So the idea is the prover now sends all the midpoints of this transition spaced with T over K steps each to the verifier. So this is efficient if K is small. And then they now only have to verify that the K pairs of endpoints are correctly specified according to the Turing machine rule. And this, in some sense, is going to be via something, even though it's not very clear why at this point. Because if you do the naive idea, like now the prover sends all the hidden tableau, it will mean it sends K chunks of the matrices h of size t over k times s. So in the end, that's going to cost you the same as sending the entire tableau. This will give us no saving. We call it the naive batching. You're just going to verify all the statements in this batch of size k naively separately. But it turns out you don't have to do this. You can verify k statements with a cost that's much smaller than k. And in fact, you can get all the way down to polylog k for UP, which is a subclass of NP. And I'm going to explain slightly how this works. Does this general picture make sense?
Well, okay, verification, but what's the step or time cost for each verification?
Yes, so we are going to recurse to a smaller problem size, and the cost of the verification is going to be that smaller protocol. And then this smaller protocol is going to be built from recursion. Yes. And we are doing it more efficiently than previous papers. Okay, but before I introduce the actual dirty stuff, this is a very clean picture of the setting of trying to batch verify proofs. We want to batch all the statements. So the setting is, let us consider NP. We will have k statements, x1 to xn. Each of them are of length n. And we want to accept if and only if all of them are true. So in this case, you want to reject because there's one of them that's false. Trivially, you just verify them separately. For NP, that would mean the prover send all the k witnesses, and that will require communicating m times k bits if m is the length of one witness. And surprisingly, this is the best protocol we have for NP. And there was a previous work from 2024 that's very interesting, highly recommended. They study this problem and they show that this is unlikely to be possible. Like if you want to get something that's sublinear in K, or I should say more specifically, if you want to get something that's sufficiently sublinear in K, then it's going to imply some unlikely complexity consequences, even though I think there's still space for studying this question. However, if we restrict to some subclass,
Or
it's something like polynomial hierarchy collapses.
I mean,
Uh,
when you are saying this impossibility, will you need for example, under certain crypto assumptions, this is doable, right? We have
yes, if you assume NP equals UP, then this is doable.
about proofs only.
Yeah,
Sorry.
yeah, indeed. Yeah, but they show something like if you can do it with proof, then it implies something like polynomial hierarchy collapses. But yes, yes. But I also want to clarify their implication. I think that's not exactly pH collapses, so I think there's still hope that we can get it. But
WI, right?
yeah, exactly. It's called SWI. Yes, yeah. It's a very interesting class, but I think it's like not formalized until this work, which was 2 years ago. So
Is like better known, but you are saying this at least this is larger than SEK.
yes,
Because it's bigger. WI is bigger.
yes, you can say if you want to be super precise, they are not comparable because in SEK, we don't really have a witness. But SWI, yeah.
For unique witness language, then I mean for unique witness language, SWI is true automatically.
Yeah, exactly.
But still SDK is like not true.
Yeah. Okay. Anyway, the bottom line that I want to mention is Bash MP is currently very widely open. But for UP, which is a subclass of NP where you are guaranteed that at most one witness exists if the statement is true, then we can actually do super efficient batching, where the communication and the verifier work is roughly polylog k times the length of the witness. Okay. And to give you also like a straw man example of how to construct batch proofs, you can assume probabilistic checkable proofs. If you are not familiar, I'll define it, don't worry. Here, the statement and witness pair is written as xiyi, and you concatenate all the witness into some vector w. So this will consist of all the y's, and you use this heavy hammer called probabilistic checkable proofs. It makes it slightly longer, polynomially longer, such that now in order for the verifier to verify that the statement is true, it doesn't need to read the entire witness anymore. Now it only reads locally like polylog k many symbols. And in fact, I think the best PCP you can get is something like 3 symbols, but the exact numbers is not going to matter for our talk. And you can imagine the verifier only reads these symbols, but because the witness length, which is pi here, is still going to be proportional to w, to the length of w, which is proportional to k. The prover can't really send the vector to the verifier. So instead, the verifier asks the prover to give it these 3 particular locations, and then the prover will send back the symbols on these 3 locations. So you can see this is super efficient. It's roughly polylog k communication. Can the verifier believe the prover? This is actually an insecure protocol. It's because when we talk about PCP, we usually assume the PCP is already written in the sky, and after the prover writes down the proof, it cannot change it. But without sending the actual proof, the prover can actually adaptively decide what to answer when queried by the verifier. So this means its strategy does not necessarily correspond to some fixed pi. And in that case, we can't rely on the soundness of PCP to prove that it's sound. And this is actually not sound. Okay. But the first protocol that shows this is possible actually relies on something similar to this, but they combine with some very interesting ideas that I'll mention later too, to make it work. Yeah. And I think the general idea is like, how do we construct this oracle where the prover is committed to the string but without really sending the string in the clear. And this is exactly the distinction between statistical proofs and arguments, because there we can have like Merkle proofs which commit to statements without sending them. Okay, let us come back to our original setting. We are trying to verify that k transition claims are correct, and each of them is of length t. So I changed the symbol. Now it's each length t, and the goal is to construct a protocol of verifying length t times k computation. So you can imagine x2 would equal to y1 if these batch of statements are actually like the things that you get from breaking one transition into k claims. And we'll recursively construct such an object. So our goal is to verify that all of them are correct. And assuming that we have this protocol, we are expecting it to output a short, small depth circuit psi. And after having this circuit, we can just evaluate this circuit on the original vector. And based on whether the circuit outputs 1 or 0, we will decide whether we accept or reject. And the point is that this psi is going to be much smaller than the original thing that we are trying to verify. And again, we have this restriction where the verifier never accesses the input x in the protocol, and only this final output predicate access the input. So we already have such a protocol. It's the GKR protocol that I mentioned. where we can use GKR protocol to try to perform this task. Imagine all the V's are the NP verifiers of each of the statements. We are just going to construct this circuit, and it's very structured, so we don't have to really write down the entire circuit. We can tell whether each of the gate it belongs to like which part, and which of the gate is an AND gate, so it's like log space uniform. So we can run GKR on this circuit. And it gives us the output predicate nicely. But the issue is the depth is going to be proportional to t, but we want something that's like better than t when t is large. Okay. And the GKR protocol, to recall, it roughly equals the cost of the verifier in GKR roughly equals the depth of the circuit. So in this case, it's t plus log k. And the cost of the output predicate, which the verifier hasn't evaluated yet, it's just output a description of such a circuit. It's going to be roughly reading all the statements and then doing some encoding checks, multilinear extension checks. And it's going to be roughly k times s, if s is the length of one witness. So this is our baseline in our entire construction. And this is actually nice if t is very small. Let's say t is n, then we are done. We already have doubly efficient proof for t equals n. But we want to support t's that are potentially super polynomial. Okay.
Wait, what's the problem? If t is a super polynomial, but when you are talking about doubly efficient protocol, your protocol could be linear in t, right? So why super polynomial t is a problem?
Super polynomial t. It's because the cost of this verifier is going to be super polynomial, right? If t is super polynomial.
This is what t plus log k.
It's the cost of the verifier of this protocol.
Okay,
Yes.
Well, can you remind me why the depth of this circuit is t plus log k? Why there is a t?
I see. So if the V's are the Turing machine transition verifier that came from Cook-Levin reduction, it's roughly checking each of the tableau adjacent tableaus are consistent. So you want to check all the symbols are equal except where the head moves. And there would be t such checks. Yes, actually
t is the tableau size.
t is the so yeah, let me go back to the picture. If
The rows in the tableau.
it's the number of columns, yes. So for example, if we want to verify the first,
Your V is to just verify each tau I.
yes, without having tau, it has to generate the tau on its own to simulate the Turing machine, and that's where what gives you t.
I want to mapping. You draw a circuit with V as a subcircuit.
Yes.
To see how that V correspond to something here. It corresponds to the checking of each tableau.
Each tableau.
All the steps in the tableau.
Yes. And it's also very important the circuit takes in just the endpoints. It generates the tableau on its own. Yes.
So the V in your next slide should be understood as first generating all the tableaus.
Yes.
Then do the verification.
Yes.
Okay.
Yeah, I should have defined it more clear.
Let me clarify what is xi and yi. Xi and yi should be just the first column and the last column for each.
Yes.
Okay, good.
So
I see.
Yeah.
Sure.
Yes, but to recap where we are now, we apply GKR to this big circuit. We don't want to pay we don't want to pay verification cost proportional to t because that's trivial Like the verifier could have just emulated the Turing machine on its own.
This is the idea from this triple R paper?
No, we haven't reached there yet.
This is some folklore technique. Everyone
Yeah, you can say that it's
It
folklore.
just rests on one single observation that GKR protocol can be like has a property that you can defer the access to S until they run it.
Yes, and
That's it.
yes, and this is very crucial for our work, as you'll see later. And I think even RL also does something like this. But that's what make their model super complicated. I think our paper is arguably simpler, but it's also still very complicated.
UP, uniqueness.
No, we haven't reached there yet. But yeah, in this picture, there's no witness. Like the X and Y's are just the endpoints. Yes. But you can imagine if you use this to build batch MP, it's going to create a lot of issues. So we haven't reached there yet. Okay. And our goal is to try to maintain the invariant that the depths that appear in the circuit that we run GKR on are all going to be very small. And if T is already very small, this gives us something efficient. But we are going to do some general like depth reduction interactive procedure that reduces the depth of the circuit that appear in the protocol. So now let us give ourselves easier lives. T is now very big, but K is exactly 1. So there's only one pair of endpoints. In this case, we can actually do the following. The prover, it's exactly what we saw just now. The prover computes the midpoints and then send all the midpoints to the verifier. This is actually acceptable if the number of the batch size is polynomial. So we have successfully reduced the depth by a factor of lambda if lambda is the size of the batch, but we increase the batch size by a factor of lambda. This is kind of acceptable because our main goal is to reduce the depth. And we have some other techniques to reduce the batch size later. Okay, and let us introduce this pictorial aid. It's all the rows in this picture are going to be the X and Y's in the previous slides. And so this K by 2 matrix is going to be the input of the batch statement that we are working with. So each box is going to correspond to one Turing machine tape. So what I mentioned was if the prover introduces all the intermediate steps. So in the previous picture, in this picture we have like one pair of X and Y. So we introduced lambda new midpoints configurations. But if we have K pairs of such things, when the prover does the same trick, it's going to introduce K times lambda many midpoints configurations for each of the statements. And this is going to create an issue. But okay. But in any case, if we try to do the same trick, we can still try to do this reduction, but we are reducing to T over lambda depth and K times lambda many statements. Okay, sorry, I'm a bit messed up, but does everything make sense up to now? If there's anything that's unclear.
I think I don't understand the meaning of the box. So K, when you say K is a
So yeah, let me go back. So here, if k equals 1, we have one pair of endpoints, and we can introduce all the midpoints. And this is okay because we can send all the midpoints when k is 1. The number of midpoints that we are sending is exactly going to be lambda, and we assume lambda is small.
batch. I think batch size.
Oh, yes.
Yeah, K is not batch size. K is number of batches.
K is basically the number of V's,
Batches.
number of batches.
Yeah. What is batch size?
Batch size, I think they are the same in this talk. Yeah. So the setting is we have K statements, and K is the batch size and number of batches. Yeah.
I should assume K squared equals T.
K squared equals T. K is some general parameter that we'll set later.
No. No. Batch size times number of batches should equals to T. That's a
Oh, yes. So we have only one batch, and we have only one batch. If the number of batches is greater than one, we flatten it to one batch, and batch size is the parameter that we are keeping track of.
Batch size is how many steps in each batch, right?
So yes, so let me.
Yeah, how do you define batch
So
size?
T is the yes, and K is the number of such pairs of endpoints.
Yeah.
Yes, and these are the two parameters. There's no other parameter.
So when you say batch size, I should
Think of K.
Number of batches.
Number of statements.
Oh, I see my computer. Okay. Your batch size basically how many xi's are contained in one x. You call that batch size.
Yes.
Oh, sorry. Okay, then please go to the boxes. Right? Okay, you have batch size 1, then depth is. So lambda is an extra parameter you introduced.
Yes.
To do this flattening.
Yes, exactly.
Okay.
And when we do this flattening, the prover must specify the midpoints. Otherwise, the statements wouldn't be ill-defined from the verifier's perspective. So that's going to give us lambda communication.
Then can go to next.
Yes.
Here, each black box represent a column in the tableau.
Yes. So each of these column is going to correspond to one black box, and then the last case that we consider, we have one x and one y that will correspond to this matrix, but with only one row.
So I should assume that the second box, in principle, should be equal to the first box in the next row.
Yes. But this is not going to hold afterwards. This is only going to hold in. Even in the honest case, it's not going to hold later when we do some random things. Yeah.
Instead of put them as this shape, you can put them just as one line.
Yes. Yeah. If we do that, anyway, I think, I want to, when we do this splitting, we are introducing lambda many states. That will expand each of the two columns into a wider matrix. And then, but here the prover cannot really send this like middle orange-ish part because k might be very large at this point. Like when k is 1, we can send it in the clear, but when k is like super polynomial, the prover cannot afford to send the meat of the matrix in this picture. But if we assume that's not an issue, we can reorganize this matrix into. I think this is exactly what you're saying. Like lambda of the many rows can be reorganized into one row of the left matrix. If you do this like perspective change, then you are going to work with a new batch of statements where the length of the transition is divided by lambda, but the batch size is increased by a factor of lambda.
No, what is the new input part?
So the thing on the right and the thing on the left, they are the same thing, the same stuff, just organized differently. So I'm just giving it a name, call it X new, because we are going to recursively run this protocol.
How do you reorganize? Just stack the second two columns on the first below the first two columns, or I mean, how do I organize? Does it matter, or it doesn't matter?
It doesn't matter. No.
Okay.
But you need to duplicate a thing in the middle because it's both a beginning and an end in different statements. Yes. Yes, but I guess when we do this, we can still perform this expansion like idea, and then we recurse to a different setting where the length is reduced, but the number of the batch size is increased. And if we denote the cost of a protocol with this function cost tk, that would mean cost tk is equal to cost t over lambda comma k times lambda, and the depth of the verifier circuit that we are working with is going to be smaller, hopefully. Okay, so this is what we are working. It's a general case where k can be large. The issue is very similar. We are still working with this batch setting, and yeah, this is the RR16 idea. The idea is to try to do a subsampling of the number of the rows. Maybe you just pick Q random rows of the matrix, and then you ask the prover to send a witness corresponding to those rows, and you check exactly those rows. And the probability that you catch a cheating prover would roughly correspond to this expression. And it's just binomial sum. And so if you know that a constant fraction of the statements are false, then you only need to query constantly many rows of the matrix.
So what's the relation of this part and the previous idea? I think I just understood the previous idea. You can reorganize to reduce basically the first parameter of the cost, because you don't care about the second parameter of cost, because anyway you have a polynomial on that.
Yes.
But you can reduce the t to t divided by n.
Yes. Yes, I think the next part is, yes, sorry for the confusion. I am trying to reduce k as well in the next steps, because if we can do this indefinitely, but k is going to blow up every time.
But you have your cost function is t plus polylog on k, right?
Yes.
I mean, as long as you put a log or on k, how large of k, you don't care, even if k is exponential.
Yes, you're right. The actual reason is that the statements in this x new is not fully defined. Like the prover is not really sending the intermediate configurations in this picture. So if you want to run GKL, you really want to know the statements.
I think you use the fact that you don't need to know is the statements until the end of the subject. Does that help?
Or I should say that, yeah, yes, I think you're right. It's just I need to rephrase my whole answer. If you use GKL, you need the input to be committed in an oracle.
Yeah.
Yes, that's the point. So here, here these configurations, there's no restriction on how they look like, and verifier doesn't have access to these configurations in an oracle. Like it's going to postpone its access, but you still need them to be well defined.
I see. Okay. Now the next part is about how to define them, or you want to first compress them, because
Yes.
after compression, your definition will be efficient. Otherwise, you're going to define something like that. Sorry.
Yeah, so they're kind of intertwined. I want to both compress it and build this oracle, and we have to do them in every time we do this. Yes, but this is exactly what the RL16 paper does. They try to, when you try to do this compression, you're doing this subsampling on the statements. But it only works when you have reasonably good distance on the statement. Namely, you know already that many of them are false. If there's like one of them that's false, then the number of rows that you query is going to be proportional to the number of statements, which will be inefficient.
I think this sentence needs some explanation. I cannot connect the good part in the statement with the black boxes in the circuit. You can explain that a little bit. Black boxes are intermediate.
Yes, so if you think of the orange matrix as the witnesses, so each of the rows are witnesses of the transition, then I'm going to subsample the rows. I ask the prover, even though I don't have access to them, I will ask the prover to send like constantly many of them to me, and then I'll check on them. But this only works when you know already that many of them are wrong. If exactly one of them are wrong, then the prover is going to cheat on exactly.
Same thing. Many of them are wrong. The means the intermediate states, basically the box. But on the next slide, you're drawing statements. These are statements. I mean, of course, the intermediate state of the Turing machine depend on the input statements.
Yes.
But they are not the same. Are you implying that if the input has enough wrong parts, then can your intermediate states be wrong?
So when I say the statement is false or the two endpoints are false statements, I mean when you run the Turing machine, you are not going to reach the endpoint. You are going to reach something else. That means there's no completion of this row, right? There doesn't exist a valid completion of the row such that it corresponds to the Turing machine transition.
Yeah, but for that to be true, you only need one of the xi to be false.
Yes.
But I think you are saying that there should be enough wrong x.
Yes, if you know that for some reason enough of them are wrong, then you don't have to do anything. You just subsample and you successfully reduce the number of statements. This is like case one.
Yeah.
Yes.
But I think you are implicitly using some condition that the more wrong xi's are there, the more wrong orange blocks. Are you doing something like that?
I'm going to use something like that, but I'm not using it yet.
Then what's the statement you want to make here? If these statements are,
If D of them are wrong, then just based on random sampling, you are going to touch one of them with constant probability if you sample.
Confusion is here you are talking about these statements are wrong.
Yes.
But that's not the thing you are random sampling. You are random sampling these blocks, right?
Blocks.
The orange blocks and the black blocks.
The
brick cells. Yeah.
Yeah. So I have K statements, K pair of endpoints. I'm going to tell the prover randomly send me a subset of them, the completion, and I only check those completions are legitimate. This is my proposal.
I see. Oh, I think I understand now.
I see.
Because the black ones are always X, I, Y, I.
Yes.
Your checking is only within only for this XIY pairs. You cannot check, for example, you cannot check one orange block from the first block and another orange block for the second.
Yes, yes.
They don't have any relation.
Yes, and yes.
Okay. See, actually.
It's because when we do this subsampling, they are going to appear everywhere in the tableau. They might be disconnected.
Okay.
Yes. But when you rearrange them, like they have some relation, but when you subsample, they break down and they become independent things. But they all correspond to the original Turing machine. Yes. Okay, anyway, so this is a very basic, like first proposal. We just subsample. This only works when we know sufficiently many of the statements are wrong. And wrong just means the pair of configurations are not legitimate. But again, D can be as small as 1. If D is exactly 1, then the number of statements that you need would be proportional to K. So we are back to square 1. And the idea here is to add a new check. So we want to enforce some stronger constraint, stricter constraint over all the configurations in this batch. In the beginning, they were independent, as you said, like if one of them are false, then there's no hope of getting anything. But we can enforce a joint constraint over them using interaction. And after that, we can ensure that actually many of them are going to be wrong with respect to this harsher, stricter constraint. Okay, and the tool that we'll actually use when we do this subsampling is called interactive proof of proximity. I think, yeah, just think of it as a method of quickly testing whether this matrix that we are checking satisfy the constraint phi. And the way that we do it is to do some like Reed-Muller thing. But in the end, the verifier has access to some new constraint on a submatrix of the original matrix. And the verifier only apply this smaller constraint, smaller circuit on this matrix. And it uses this to decide whether it accepts the original matrix. So this is another black box that we are using. It's called interactive proof of proximity. But I also have a pictorial. Okay, I think this is a bit too technical. It's exactly what I said. You have a matrix. You want to test whether it satisfies some constraint specified by a predicate circuit. In interactive proof of proximity is a protocol that produces a subset of the matrix such that the number of rows is sufficiently reduced by a factor of D. And it also outputs another predicate that only applies on that local subset. And the verifier doesn't access the original matrix throughout the protocol. And the cost of this protocol is going to be proportional to the depth of the original predicate. Yes. So if this doesn't make sense, which is probably the case, just look at the following picture. In the matrix, we have this matrix of statements. We want to test whether it satisfies some predicate phi. Supposedly, many of the rows contain errors. IPP is just a protocol that reduces the number of rows and also outputs another circuit such that if you check whether the new matrix satisfies this new circuit, you will know whether the original thing is close to the original circuit. So the sounder says if the matrix is sufficiently far, then with high probability you are going to get something that would be falsified in the end. Okay.
In the language of IPP, what is D?
What is D? D is a distance parameter. So it's how many rows are guaranteed to be wrong.
Okay.
Yes, so we can try to run IPP. So it's a fancier way of doing the subsampling that I mentioned. I construct this circuit first. It checks that all the pair of transitions are correct. But the IPP cost is going to be proportional to the depth of the circuit. It's very similar to GKL. And also the row distance might be 1 because in the original batch setting, maybe you only have one false statement. And in that case, IPP doesn't give you anything. So this is the same thing as doing the subsampling, just like replace using IPP. And the reason why we use IPP instead of doing the random subsampling is because we are going to construct a more complicated circuit that cannot be like subsampled without using the machinery of IPP. So actually, how do we construct this shallow circuit that has distance? We are going to use recursion, and we'll try to run another instance of our own protocol, but with some smaller T prime and K prime. And again, this is a recap of what I mentioned. Sorry for jumping back and forth, but if you have one pair of statements, you want to verify all of them are correct. The prover introduce all the midpoint states, and then you increase the batch size. But the prover is not going to send the midpoints because we have many instances now. But we do this perspective change. Yeah, you already saw these slides. And as we just said, the issue of doing this is because when we run the recursed version of our own instance, we actually need the input states to be well defined. But without the prover sending the midpoint states, we don't really know the k times lambda new statements in the clear. They are not enclosed in an oracle. So we cannot apply the soundness of our induction hypothesis in the recursion. And this is the issue. And the way we solve it is to manually create this effective oracle or commitment using error correction. And this is the main idea from the 2016 paper. They built this seemingly impossible, statistically binding, but still shrinking commitment. So you see the quotation mark, it's not actually the commitment from Merkle tree. The way they do this is to, for each of the column of the matrix, compute some error correcting checksums. So think of XOR of the rows. And the prover doesn't send the entire matrix. It's going to send just the checksum. And the checksum is going to be very small relative to the number of instances in the batch. And other will now add consistency checks of the checksum. So if other has access to the input matrix, it will make sure all the columns have the checksums that the prover committed to. So the reason why this helps is because now if the prover, if some row are wrong, then the prover has to alter that particular row somewhere. And that would mean it has to alter at least D rows because the code consistency checks ensure that all the code words are distance D apart from each other. So if the code consistency check passes, then the matrix must be modified on at least D rows. And this allows us to uniquely define some M star that the prover committed to if it sends us such commitments, such checksums. It's going to be exactly the unique point within the decoding radius of the code that has the checksum. And M is just a prescribed unique witness that you should send if the prover is honest, which correspond to the actual midpoints the prover would send. If the prover doesn't send the correct checksum, then it will be committing to some other set of configurations within distance D from the from the correct configurations. Yes, but with this technique, other effectively gains Oracle access to one point in this ball, and yes.
Yeah, I was
This.
trying to clarify. So if M star, sorry, if the checksum is honestly generated, then we don't care. But as long as it's dishonest, then it at least has a distance of D, which you can handle using the
IPP, yes. If the prover is cheating outside the ball, then we would subsample and catch the prover. If the prover is cheating within the ball, then we can somehow extract this M star because it's now committing to this M star. And if we can extract it, then we can rely on the soundness of our subprotocol. So this is very.
Oh, we are saying extracting.
It means in the soundness analysis, I can define the. So the reason why.
Define a unique M star.
Yes.
You need to break the underlying sound
Yes.
of soundtrack.
Of the subprotocol.
I see. Of that orange block, black.
Yes, the X new thing. Yes. So yeah, but I think the most exciting part of this technique is that they realize if you have some uniqueness of the witness M, then you can ask the prover to commit to one point in its in some radius corresponding to this N. Like
Is this the idea of current paper or your previous paper?
this is from the 2016. Yes.
FOCS?
I think either stock or FOCS, I forgot. Yeah, 2016. From RRR 16.
Oh,
Yes, yes.
I see.
Yes, but as you can see, if we are working with NP where we have like too many statements, then we cannot do this extraction confidently. We wouldn't know what the prover is cheating with respect to.
Okay.
Yes. So this crucially rely on the Turing machine being deterministic, because we can like define this M by just simulating the Turing machine. Okay. So this is, yes, I think this also is related to your question. When we do this like Oracle building thing, prover would insert a witness as we described, and it sends a checksum, and it effectively binds it to some matrix within the ball. And then because it's bound to that matrix, we can now run our subprotocol on this submatrix. And it actually has like more instances, but the depth is reduced, so hopefully we'll get better efficiency. And this soundness relies on being able to argue about this extraction. Okay. So the final GKR that we are going to run, or the final protocol that we are going to run, is to run IPP on this predicate that not only checks our subprotocol accepts the matrix, it also checks the matrix is opening correctly to the checksum. And if we know the checksum is error correcting, then that would mean by the soundness of our subprotocol, that would mean the M star that we extracted from the protocol is going to be rejected.
Still like RRR 26 paper 2020.
Oh, this is actually from our paper.
Yeah. Can you tell me where do we start to see the materials from your paper? Where is the line?
They are completely different. It's the two are the
Cool.
Yes.
Then here, are you just elaborating on the soundness proof? basically you're explaining that part in detail when the M star is out of the D ball and within the D ball, how do you handle things?
Yes.
Yeah, you're explaining that part.
Yes.
Okay.
And yes,
I
and
thought you are already starting something new.
as yes, I'm wrapping up the protocol. Yes. Um, so after running this recursive step and the commitment step of the checksum, we get this predicate from our recursion assumption, and this predicate is going to be rejecting on the prover committed M star in the ball. That would mean we get distance on the IPP. And then in that case, we can actually run the IPP with respect to the more complicated check. So it's no longer the simple a bunch of V's on top, you add an AND. It's going to do this like checksum check as well as the recursion check. Yes, so now IPP soundness now works. And we successfully reduced the size of the matrix by a factor of D. So just to summarize everything, it's actually going to be very simple. I think I did too much motivation and soundness analysis, but the protocol is actually very simple at a very high level. First, the prover commits the midpoint matrix and send a checksum of the columns. And then the first recursive call we do is to call on this like matrix with more rows but shorter transition. And after that we get another predicate, and we run IPP on that predicate and the checksum check, and that will allow us to reduce the k times lambda to something much smaller than the original k. And in that case, we can do another recursion to the reduce some matrix from the IPP. So now we actually reduce the batch size of the matrix, the number of rows in the matrix. Yes, so it's kind of like a four-step protocol if once you understand all the black boxes. And then I think that it might be one point of confusion is there are a lot of parameters to keep track of. So let me try to just show you why we get our efficiency in the end. When you unwind the recursion, it's going to look like this, but it has a very nice pictorial interpretation. If you use the x-axis as the length of the transition and the y-axis as the number of the batch size in the claim, each of our core, like when transition length is t and the number of statements is 1, we are going to do the midpoint split first. And here the prover explicitly send all the midpoints, and we are going to this t over lambda, comma lambda case. And then the next step would do a more complicated two-way recursion that involves IPP commitment and all those steps. And then you do this again on all the recursion. And it turns out if you try to solve that recursion, the final cost is going to be roughly the number of paths that you can get from this starting point to the left boundary of the plane or the y-axis. So this is known also as the Catalan number, if you denote L as log lambda t, and then it has roughly 2 to the L in asymptotics, and then you balance the two terms. In the end, you get 2 to the square root of log t. That means we get a verifier that runs in 2 to the times square, 2 to the square root of log t time. And this is very abstract, but our dream is to get something like polylog t. And the trivial case would be to have something like t, which is 2 to the log t. So we are kind of halfway in between if you think of the exponent as measuring the progress. Okay. And just to mention, the paper from last year got something like 2 to a log t to the 2/3. So the improvement is dropping from 2/3 to 1/2 in the exponent. Yes, but this will be the end of my talk, and thanks for all the questions and clarification.